Welcome once again to the lecture of separation axiom from topology. So we are moving ahead. One important theorem is left from the topic of house of spaces, and then we will move on to the next topic, that is the regular spaces and T3 spaces. But before moving on to the regular spaces and T3 spaces, the last theorem that is required for the house of spaces, I am going to prove it here. The theorem is, write down the statement of the theorem first of all. So if f from x to y is an onto and open map, here x is a topological space, y is a topological space, the function f from x to y is onto as well as open, and the set A of all points x, y of the type fx is equal to fy. So x and y are both points of x. So it is a point of x cross x. So it is a point of x cross x such that image of first element is equal to the image of second element. This set is given to be closed, is a closed set. This is given. Then y is a T2 space, is a housed of space. This we need to show. Now let us move on to the proof of this theorem. So I am moving on to the proof. We actually want to prove that y is a T2 space. So from where we have to start? We will have to take two distinct points from the set y. Y is here. So fx to y is a function. So whatever the point in y you will take, it is an onto map. It is given. It is an onto map. So that means every point is image of some point of x. So if you want to take two distinct points from here, you can take f of x and f of y. You can take f of a and f of b. So let f of x not equal to f of y be 2 points of y. This I can take because f from x to y is onto. That is the reason why I am taking 2 points from y as fx and fy. And these are two distinct points because we have to follow the condition of Hausdorff space. We will have to take two distinct points from the set y, and then we will have to find two open sets in y such that one open set contains fx, the other contains fy, and their intersection is y. That means the two open sets are disjoint. This we will have to obtain. So I have taken 2 points fx and fy from the set y. Now if fx is equal to fy, then xy belongs to a. Here fx is not equal to fy. This means your xy does not belong to a. And this point does not belong to a means where this point is, this is in a complement. This is in a complement. A is given to be closed. That means a complement is open. So this is a point of an open set. Therefore, by definition of open sets, you can have a neighborhood between these two. So you can say there exist open sets G and H in X such that your xy belongs to G cross H, and G cross H is a subset of A complement. Now, G cross H is a subset of A complement clearly implies that G cross H intersection with A is phi. This is phi. This is clear because G cross H is a subset of A complement. Now, xy belongs to G cross H means your x belongs to G and your y belongs to H. x belongs to G means your fx belongs to f of G and your fy belongs to f of H. What about fg? G is an open set, H is also an open set, and the function f is given to be an open map. That means your f of G is also an open set in Y. F of H is also an open set in Y. So what you have obtained? You have taken two distinct points fx and fy from the set Y, and you have obtained two open sets fg and fh, one containing fx, other open sets containing fy, and fg intersection with fh is phi. Why this is phi? This portion I am leaving as an exercise for you, but I am giving you the hint. To prove this, you will have to use this. To prove that fg intersection fh is phi, you will have to use this fact, that g cross h intersection with a is phi. Use this and then you will be able to prove that fg intersection fh is phi. That means you have obtained two open sets, one containing fx, one containing fy, and their intersection is phi. That means that space Y is your Hausdorff space. And that was the theorem where I wanted to finish this chapter, this topic, not the chapter. And now I am moving on to the next topic, that is regular spaces. So we have now completed T0 spaces, T1 spaces, and T2 spaces. Now we are going towards regular spaces. Regular spaces. Just to re-memorize what we have done till now. Till now, there is a topological space X tau. X is the set, tau is the topology. Always we start with taking two different points x and y. X not equal to y. If we are able to find an open set containing x and not containing y, or we are able to find an open set y not containing x, that makes the topological space T0. If this is OR here, this is OR here, either an open set G containing x not containing y, or an open set H containing y not containing x, the space is T0. If we are able to find both these sets, open set G containing x and open set H containing y, G not containing y, H not containing x, then the space is T1. That means a Fletcher space. The third condition is, if we are able to find these two sets G and H, G containing x, H containing y, such that G intersection H is phi also, that means G and H are disjoint, then we say that the space is T2 space, that means the Hausdorff space. And now we are moving towards the next one, that is the regular space. What a regular space is now. So for regular spaces, what we are to take and where we are to reach. Again, we are having X with topology tau on it defined. This time we are not going to take two distinct points X and Y. This time we will take one closed set F and a point X not belonging to F. So what we are taking, if for every closed set F and a point X belonging to X such that X does not belong to F, we have, what we have now? The condition is now we have, for every closed set F and for every point X not belonging to F, if we are having two disjoint open sets G and H. G is here, G contains F, and H is here, H contains X, such that G intersection H is again phi, then we say that the space is regular space. So what we are to write here in theory, we have open sets open sets G and H such that your earlier it was that X belongs to G, Y belongs to H. This time it is your X belongs to G and F is a subset of H with an additional condition that G intersection H is phi. That means G and H are disjoint sets. Then we say that the space X top is regular. So this is the definition of a regular space. Earlier we have named the topological spaces as T0, T1, T2. Now not it is C3, it is regular. A regular space and T3 space, these are two distinct things. What the distinction between these two? I am going to clear that distinction between regular spaces and T3 spaces. First of all, you will have to understand that a T3 space, a regular space need not be a T1 space. In fact, it need not be a T0 space. It need not be a T2 space. And one example will serve for all these three theorems. You can take the set X as the set containing three elements ABC, and you can have a topology on it as phi, the singleton set A, the double set BC, and the whole set X. Now this is the topology, this is the set, and the good thing is that this topological space is regular, but it is neither T0 nor T1 nor T2. Why? How? So here, if I am going to prove that this is a regular space, what I am to do, I will have to take one closed set from this set. So here what the closed sets are: complement of phi is X, complement of A is the set containing 2 points B and C, complement of BC is A, and complement of X is phi. So these are the four closed sets. So whatever the closed sets you want to have, you have. Suppose I am taking X as a closed set, then what I need an additional, a point which does not belong to this closed set, and this is not possible because X is a whole space. So this I cannot take as F. So move to the next one. Let it be your F. So let F be your set BC. And now what you want? You want a point that does not belong to this set, and that is clearly the point A. So I can take X here as A because A does not belong to your set F. F means the set containing 2 points B and C. Now what you need at all? You need two open sets, one containing the point X, that means A, the other set containing whole of the set, closed set, that is F, such that the two open sets are disjoint, their intersection is phi, then the space will become regular. And this is very much obvious, very much clear, because two open sets, here the open sets are these four. This is one open set, the second one, the third one, and the fourth one. For the set containing F, I will take this as the open set, the set BC. So this is the open set that contains your set F, because F is wholly contained in BC. F is in fact the set containing 2 points B and C. On the other hand, for the point A, I am having this set, the singleton set A. This is the open set. This is your H. This is your G. Your G contains A. Your H contains F. And intersection of your G and H is phi, which makes this topological space regular. So this is a regular topological space, but this is not T1, this is not T0, this is not T2. Why? So that is also very much obvious, very clear. So if you take any 2 points from here, suppose you are taking A and B, or you are taking B and C, or you are taking A and C. Whatever the 2 points you are taking, suppose you are taking A and B. Now to make the space T0, so T0 it will be, I have to talk about, but this condition should be satisfied for all. So I'll take these two only. I'll take B and C. I'm not taking A and B or A and C. So I'm taking the points B and C. If this topological space is to be T0, then you will have to have an open set which contains B but not C, or an open set that contains C but not B. these are the four open sets. This open set, this does not contain either of these two. This is the open set, this does not contain either of these two. This is the open set, but it contains both of these. This is the open set, this contains both of these. But what I want an open set which contains one of the elements and not contain the other. So this condition is not possible here. So this is not a T0 space. Similarly, it is not a T1 space, because if a space is not T0, how it can be T1? Because in T0 you are having the condition OR, and for the topological space to be T1 you are having the condition to be AND. Or if the OR condition is not satisfied, how AND condition can be satisfied? That means if you are not having G or H, how can you have G and H? So this condition is not possible. And thirdly, it is not T0, T2. Why? Because if G and H are not existing, T2 is having more strong condition. T2 is having that you should have two open sets which are disjoint. Here, in fact, the two open sets are not existing, from where we can have two disjoint sets. So it is not T2 space either. So a regular space need not be T0, need not be T1, need not be T2. So after T0, T1 and T2 spaces, it is obvious that it comes to our mind that what is T3 space. So a T3 space is a space which is regular as well as T1. If a topological space is regular and is also T1, then we say that it is a T3 space. So for a topological space to be T3 space, it must be regular as well as T1. So this is the definition of T3 space. Earlier we have defined regular spaces, and now I have defined T3 spaces. So I'll just move on to one or two short theorems and then I'll stop the video, and then we'll move on to the next topic. So before going there, one example. So first example that is very much clear, that the set of real numbers with usual topology is regular. This is regular. And the proof is very easy. The proof is what you have to take. You have to take a closed set. And what is a closed set in R with usual topology? It is either a closed interval or it is finite union of closed sets. So RU is a regular space. This I will prove later on, because a little bit more knowledge you need here to prove that RU is a regular space. Before going to this, I'll have to prove another theorem, that is every T3 space is T2. Every T3 space is a T2 space. I have told you just now that a regular space need not be T2, but a T3 space is T2, because T3 means regular as well as T1. Now here we are having two conditions, regular and T1. These two conditions together will make the topological space T2. That's what we need to prove here. So let X top be a T3 space. Be a T3 space. We are to show that it is a T2 space. The proof is very simple. To prove that the space is T2, start with having 2 points, 2 distinct points. So let X and Y be 2 distinct points of the set X. Now, you know that in a T1 space, because it is T3, it is also T1. In a T1 space, every singleton set is closed. In fact, every finite set is closed. So this point Y, I am converting this point Y into the singleton set Y. So this is a closed set, because it is a T3 space, so it is T1, and in a T1 space every singleton set is closed, so this is a closed set. So this set I am taking as F. Since X is not equal to Y, it is very much clear that X does not belong to this set. So what you are having now, you are having a closed set and a point that does not belong to that closed set, and the space is T3, that means regular also. So now we are to apply the condition of regular spaces, a closed set and a point that does not belong to the closed set. What your regular space set say, that there must exist two open sets G and H such that X belongs to G, your F is a subset of H, and G intersection H is phi. Now I think you must have understood we are very close to the conclusion of the theorem. Your F belongs to H. What is your F? F is your singleton set Y. Your singleton set Y is a subset of H. And singleton set Y is a subset of H means your Y belongs to H. Where you have started from? You have started from two distinct points X and Y, and now you have obtained two open sets G and H such that G contains X, Y contains H, and their intersection is phi. That means the sets are disjoint, and this makes the topological space T2. That means house of. So a T3 space is a T2, whereas T2 space need not be T3 because T2 need not be regular. So here I am going to stop this video. We'll wait for the next video and we'll have more and more theorems on regular spaces, on T3 spaces, and then we'll move on to the normal and T4 spaces. Thank you all.